It is my pleasure to introduce our next speaker for today, Senor Albert Catalan-Tatjer. He's a first-year PhD student at Alice Institute Tübingen, mentored by Jonas Geiping. So today we're getting something special. It is a world premiere of a presentation that will soon draw crowds at the poster presentation at ICLR this April. I think if ICLR had a spotlight papers this year, this paper would for sure get a spotlight. Why? Because Albert draws a spotlight onto something that many people have overlooked so far. And what is that? That is a role of training dynamics in language model robustness to post-training quantization. And as it turns out, there are quite a lot of things happening behind the scenes. So please join me in welcoming our next speaker, Mr. Senor Albert.
Thank you, Anna.
The floor is yours.
Okay, I hope I can deliver on this. Yeah. Well, thank you very much, Beno, and thank you everyone for being here. I'm going to start maybe with this world premiere. Our work with Nicolo, who's here, and Jonas, was about the training dynamics and how they impact post-training quantization. I think that this is a very nice talk to have right after your talk, because this is talking about the other axis that most of the scientists, compression and quantization scientists, don't really think about, right? For compression and quantization people, models are just something to optimize, and models are just something that they can compress and they can make more efficient. But sometimes the community that trains these models and the community that compresses these models need to get together, right? And this paper is trying to bridge the gap between what happens when you pre-train and what are the consequences of pre-training on this quantization, and maybe even for compression. I didn't check, but maybe for compression as well, right? I'm going to start by trying to explain quantization. I think you did a good job already, but this is the way I like to imagine quantization, right? You have this high frequency or high resolution signal, which is this red line, and then you're trying to compress the signal into discrete buckets or bins. And I like to imagine that quantization is just histogram binning. So you go from the red line to a discrete number of buckets. In this case, for 4-bit quantization, you would have 16 buckets. And the way one could go about quantization would be to take the red line, you match the original tensor to the range that you can represent in the quantization range, right? So you scale and shift, and then you just decide all the points that fall within the bucket are going to be represented by the number of the bucket. And then when you have to do any operation on this, you dequantize and you retrieve the full precision, and you only need to store the low bit tensor and the scale and shift to invert the operation, right? This is the most naive quantization process that you can have. And as you said, tensor transformers are very hard to quantize, and this doesn't always work. This works for 8 bits maybe, or for 16 bits, but it most certainly does not work for 2 bits, which is what people are going after lately. And people are trying to come up with these R matrices that are basically trying to rotate, as you said, rotate, scale, or do permutations on the space of the weights and the space of the activations to offshore or to make something that was originally hard to quantize. Here in this example, you can see the activations of a transformer. And this is very hard to quantize because if the range is very wide, you'll have a lot of values that will fall on the same bucket because all the buckets are going to be uniformly distributed, right? So you will only have 3 buckets that are going to be filled in the bin histogram binning example, right? And the other bins are going to be empty. And so what they do is they invent or they find these R matrices such that the activations or the weights are smooth, and it's very much easier to quantize. There are many examples, and you can read a lot of literature on why something is better or how something is better, and so on and so on. But this is not the axis that we're going to explore in this presentation. I took this slide from the BLM Europe meetup, which was in Zurich last year, where they were trying to make the case, or maybe they made the case, right? And the scaling loss people already published this, that a larger quantized model is always, they say, I took the always out, better than a smaller and quantized model, right? So in this situation, you have Quen 7 billion with 7 million parameters and Quen with 14 million parameters. And they show how quantizing the weights and activations to 8 bits, which is this blue bin, performs better than the Quen 7 billion, which is this gray bin, right? So even though they use the same number of bits, one is actually much better, which is like 9% better than the other. So quantization is very crucial because if you want to get the best performance for your compute, for your inference compute, you will probably train a larger model and then quantize back down, right? Or this is what this scaling is trying to make the case for. But we're asking a different question, right? Which is how or what makes a model more robust to quantization? How can we help the quantization people and the compression people to make their methods perform better than they should have? And there was some work that she actually mentioned in the talk before. At the beginning, people thought that transformers could not be quantized at scale, right? And this is a very nice early paper on quantization at scale, where they actually go up to 150 billion parameters, which is huge for the time. And they show how some of the decisions have a large impact on whether a model can be quantized or not. And then there are other questions and other works that ask the same question on what makes a model robust to quantization, but the question is a bit more hidden or more indirect, right? In the scaling loss paper, they're asking somehow whether the token budget hinders quantization performance, right? Or as some question before was asking, how much does it matter, or what is the impact of how much the model knows on compression or on quantization performance, right? So the token budget is some proxy for how good the model is at some task. Before I can dive in, I'm going to explain what we did, basically, right? So what we did and what I'm going to show is we define a quantization error, right? We want to understand how much is lost, which is what we're going to measure. And then we're going to quantize a lot of training trajectories of open source models and see what happens during training for the quantization performance. The way we define quantization error is with this ratio, where the theta hat is the model quantized, which is supposed to have higher loss than the quantized model, over the loss of the full precision model, -1. We define the quantization error like this because I believe that if the loss is smaller, the quantization error should be higher than even an absolute term, right? But the shape and the whole story that I'm going to show is basically the same for this definition or for just the absolute error definition, right? So what happens? I'm going to show you, and I'm going to stop a bit in this slide because you're going to see this slide for many different models later on, right? So this is small LM3, which was published last July, which is a 3 billion parameter model by Hugging Face, where they trained for 12 trillion tokens, which is a huge token budget, right? They trained for 12 trillion tokens, and the first 10 trillion tokens are with a stable learning rate. The scale they use is WSD, which is more famous here in Europe, which is some small warm-up that we don't even see, then stable learning rate, and then fast linear decay. And as you can see, here I'm showing you the number of training tokens versus the quantization error. And you can see how the quantization error is relatively stable during the stable phase of the learning rate. And as the learning rate decays, quantization error spikes up very fast. For the validation loss, something similar happens that may be opposed, right? Validation loss decreases and then it spikes back. And then we said maybe something is happening with the learning rate, right? That's the first thesis that we have. And then, if this is happening, how much does the learning rate decay or the learning rate magnitude affect? Before moving on, I want to make sure that this also happens for accuracy, right? If this phenomenon is only observed in the loss space, but in the task accuracy space, we don't observe this phenomenon, it's not as interesting of a question, right? But we see how the accuracy degradation and the loss degradation track each other relatively. The accuracy is computed on some reasoning task, language reasoning tasks. And then now I'm going to go on with some controlled experiments that we did on a 160 million parameter model on up to 100 billion tokens by isolating different parameters, right? The token budget, learning rate magnitude, weight averaging, weight decay, learning rate shapes, and so on and so on. And when we change the token budget, so these are the same parameters, right? These are the same two figures as before. You can see in purple the decay phases of the model, the learning rate decay, and in green you can see the stable phase. And you can see that when you decay, regardless of the token budget, quantization error spikes. The same way that validation loss goes down, right? So here we see, or we start seeing that maybe the learning rate actually has some dynamics or changes the model in a way that is significant for quantization performance. And now we check the learning rate magnitude, right? And we change the magnitude of the stable phase. And here I have 4 different learning rates, which are sorted by larger learning rate to smaller learning rate, right? So I train with 4 learning rates. And then this is a very important plot. This is for 4-bit quantization. This is the validation loss versus validation loss. So what you care about is for the validation loss of your model, right? You don't care for the quantization error. If your model has better validation loss at the end of the day, even if it has higher quantization error, you don't mind. You want to have, or you want to see what is the trade-off between one and the other, right? So what we do here, I'm going to focus on this, even though the story is the same or similar to this one, because it's much easier to see in this 3-bit quantization other than 4-bit quantization. And what you see here, the perfect model would have x equals y performance, right? The validation loss for the baseline, for the full precision, should be on the bottom left, and the quantized performance would be on the bottom left also, right? So horizontal means full precision performance, and vertical means quantized performance. The important thing that we see here is that the larger learning rates have lower quantization error, and the trade-off between one and the other is also better for larger learning rates. So a small learning rate of 3 minus 4 would be this one, and it really, even though it's better than the 1 in minus 2, this learning rate becomes much worse at quantization, and then it's an overall worse model for quantization, right? And the important part is that there are these 2 values that get the same point, right? 1 in minus 3, which is orange, and blue, 3 minus 3, get to the same baseline full precision validation loss, but one has a better time being quantized. And we argue, and we will argue at the end of this presentation, that this is a key insight that can make model and model builders study quantization error during routine hyperparameter tuning to choose the one that will quantize better. Moving on, we also try to understand what is the impact of weight averaging, right? There's this paper, weight averaging leads to wider optima and better generalization. In general, weight averaging has been used as a proxy to learning rate decay, and also as a way to get better minima, wider minima, and better generalization, right? So let's see what happens. What we see, same plot as before, right? This is for 4-bit, full precision quantization, and this for 3-bit quantization. And what we see is that the orange line, averaging, performs worse than the original model at full precision, but averaging actually for 3-bit quantization beats the baseline of full precision, right? Which is kind of surprising and something that's for free to do, basically, because weight averaging is defined as the aggregating averaging the checkpoints during the single trajectory, right? So here, if you average during the trajectory, you will get better quantization performance. And you never have to choose between averaging and not averaging. You can do actually both. And maybe take one for the quantized and maybe take the other for the quantized. In the top plot, you can see how the validation loss to quantized validation loss performance is much different. It's very, very much different for the average checkpoints, right? Which is very surprising. And then we ask the question, right? Everyone has to ask the question, why may that happen, right? What is the explanation? We don't know, right? This is deep learning. This is a question that you never ask, right? But we have some theories and some explanations and mental models that are definitely, there's no causal chain, but may help to paint a better picture. So since there's this idea that weight averaging leads to wider optima, right? Maybe it's all about the geometric properties of the loss. Maybe what matters here is the sharpness or flatness of the loss landscape. So this is what we check. On the 4 experiments that I showed you before, I take the loss landscape at the very last checkpoint, right? And this is the smallest learning rate, and this is the largest learning rate, right? So these pictures correspond to the top right figure. And then you can see in the 0, point, there is a star, which maybe a bit too small for you to see, but in the 0, there's a star that corresponds to the last checkpoint. On the y-axis, there's this square that corresponds to the quantized checkpoint, right? So I'm taking the slice between the last checkpoint, the last step, and then the quantized step. And in this slice, you can already see how the geometric properties of the loss are very different between the different learning rates, right? So everything is the same, but we only change the learning rate. And you can already see how the small learning rate leads to what looks like sharper minima, and large learning rate leads to wider minima, right? And then if we explore the actual top eigenvalues of the Hessian, we see that this is the quantization error, and this is the plot of the top eigenvalues of the Hessian. When we explore this, we see that as the learning rates decay, the top eigenvalue of the Hessian or the sharpness increases. And even though here there's this weird thing happening when everything goes up, right? If we zoom in, we see that for the green values, only one eigenvalue, only the top eigenvalue of the loss increases sharply, whereas the rest remains small, right? So it's only sharp in one direction. In the other directions, the loss is relatively flat. And we see for the purple, which is the decay, that many directions become much sharper, not only one. So it's basically indicating that the model is going to be less robust to weight perturbations in more directions than it was before, right? And with all of these insights, we move on to a real-world scenario where we can check the two Olmo to Furious paper. This is a screenshot from the paper where they have a 300 billion token learning rate ablation, a routine hyperparameter exploration experiment that everyone that builds a model has to do, right? Everyone here swipes on the learning rate, and this is exactly what they do. And then they swipe, and then on 300 billion tokens, and then they do a linear decay on 350 billion. And they reach the conclusion that even though some are faster than the others, when you do a linear decay, all models have an equivalent loss. I should have highlighted this, but they say equivalent training loss from all the learning rates, right? Which I think this is important because 2 slides before, I showed you that when you have the same or equivalent training loss, maybe you should check the quantization error. And you may be asked, when does that happen in real life? Maybe it never happens. Well, here we have an example from Olmo 2, 7 billion parameters, where they got into the same exact situation. And what did they do? Well, they chose the smallest learning rate. And we actually contacted the authors, and they sent us this exact same learning rate ablation, which I have here. And the same idea of the same plot before, validation loss versus validation loss. The perfect model would be x equals y. And you see how the larger learning rates are further down. It's hard to see because it's a 7 million model trained on 300 billion tokens, right? So there's not a lot of density, information density or whatnot. But still, the smallest learning rate, which is coincidentally the one that they end up choosing, is the one that has the worst trade-off between both performances. So, surprise, it happens on real life. And to summarize all of this, the key insight is that, well, this may seem obvious, right? But the key insight is that quantization is, at the end of the day, a weight perturbation. It's not some magical post-training transformation that we're doing to our model. It's just a general weight perturbation that will benefit from general model robustness ideas and recipes, which can be and are largely cited in the literature: large learning rates, maybe weight averaging, larger weight decay, and so on and so on. And finally, another key insight is that if you are Olmo or the OpenURLLM people, or if you're building a model, maybe you care about, maybe you can make your life easier when you have to quantize, right? And if you ever care about your model being quantized, maybe checking quantization performance during routine hyperparameter fine-tuning, right? Maybe then you can understand what hyperparameters will lead to better quantization performance, which is something that a lot of users are going to do to the models that you open source. And this is basically the end of the talk. Thank you very much for listening.